Welcome back. So today's lesson is about the idea of algebraic proof. We're going to be proving directly certain facts, and then you're going to have a go at doing some yourself. Maths is the only branch of science, the only branch of knowledge where we can prove things, because maths is built on some assumptions, axioms, that we assume are true, and everything else follows from those simple axioms. So one such axiom might be that all the numbers are equally spaced. All the whole numbers are equally spaced. And it seems a really trivial thing to assume, and generally the things we're talking about are trivial. Another one might be two parallel lines on a flat surface never meet. So we start with some basic assumptions like that, and we build up mathematics, all of mathematics, and all this complex and amazing and interesting stuff we build up from a few simple ideas, and we can prove these ideas because we've assumed things to be true. Now, you can't do that in the real world. You can't do that in physics. You can't assume that gravity works in a particular way and build your model around it. You have to start with the way that gravity works and build it backwards. So, for example, Newton had a very good theory of gravity, but he couldn't prove it. He could only test it. And he tested it, and he tested it, and he tested it, and it always worked. And except it didn't. He just kind of ignored Mercury. He said, Mercury, the results, the measurements aren't very good, or there's probably been a mistake somewhere because my data, my method works so well for every other planet. But it became clear that wasn't the case as we got better and better at measuring, and it was obvious that Mercury didn't quite fit Newton's model of gravity, and so we needed a better theory of gravity. So Einstein came along and refined the theory of gravity. And that's how science works, but it's not how maths works. With maths, we can say if something is true or not. And there are some open questions. We haven't answered them all yet. But we can prove things in maths that we can't do in science. Okay, so before we get started, a couple of things that might be useful. Let's say we want to talk about odd numbers or even numbers, which we're going to want to do during the course of this lesson. In general, we'll call an odd number 2n plus 1, and we'll call an even number 2n. Now, I might not state it explicitly at every point, but in general, the number n is considered as an integer. Okay, so an even integer would be 2n, and an odd one will be 2n plus 1. And then consecutive numbers can be written as, say, n plus 1, n plus 2, they'll all be consecutive, or I could write n minus 1, n plus 1 to represent 3 consecutive numbers. I'm just changing the page width. So depending on what you're doing, you might choose to represent your numbers consecutively, slightly differently. Okay, so let's get started. Okay, here's my first little thing where before we start proving anything, I'm going to show you how easy to disprove something that's not true. It's not always this easy. But if I want to disprove something that's not true, I only have to find one counterexample, one time when it doesn't work. So here I've got a claim that 2 to the power of p minus 1 is always going to be prime, providing that the power p is prime. And we can check it for some numbers, and it seems to work. 2 squared minus 1 is 4 minus 1 is 3. Prime. Works. 2 cubed minus 1 equals 8 minus 1 is 7. It works. 2 to the 5 minus 1 is 32 minus 1, 31, and it works. And we can go on like this. 2 to the 7, and it starts to look like is 128 minus 1 is 127. Now, is that prime or not? I'm pretty sure it is. I'm just going. And in fact, the next one is 2 to the 11 minus 1 is 2048 minus 1 is 2047, which is not prime. 2047 is equal to 23 times 89. And because of that one example, we can disprove the whole statement that 2 to the p minus 1 is always prime if p is prime. So that's counterexamples. You only need one counterexample to disprove something. The problem is, if this was true, I couldn't list all the examples because there'd be an infinite number of them. I'd have to do 2 to the power of every prime. So I want to be able to check that in general something is true. So this is one of my favorites. That every odd square number is one more than a multiple of 8. And if we were to try and check a couple, 1 squared is 1, which is obviously 0, 8 plus 1, so it's true. 3 squared is 9, which is obviously 1, 8 plus 1. 5 squared, oops, that's supposed to be 9. It's 25, which is 3 8 plus 1. 7 squared, 49, which is, what, 6 8 plus 1? And so on. You can see a bit of a pattern here as well. But how could we prove this completely? Well, here's what I'm going to do. First, I'm going to start with an odd number. So my odd number, 2n plus 1, and I'm going to square it. And then I'm going to take 1 away. So this number, I want to prove that this number is a multiple of 8. And it is, which I'm now going to demonstrate. So I'm going to square that out. Get 4n squared plus 4n plus 1 minus 1. Obviously, that's 4n squared plus 4n. So it's obviously true that every odd number squared is one more than a multiple of 4, because this number is divisible by 4. Hopefully that's obvious, because there's a 4 here, divisible by 4, and there's a 4 here, divisible by 4. So how do I get from there to reach the conclusion that it's not just divisible by 4, but it's actually divisible by 8? Well, I'm going to factorize it. Take 4 out as a factor. I get n squared plus n. Take n out as a factor. N times n plus 1, all multiplied by 4. And the neat thing here is that, although I don't know which one it is, one of these numbers has to be even, because they come one after each other. They're consecutive. So either the first is odd and the second is even, or the other way around. Or this one is odd, no, this one is even, and this one is odd. So that means that not only is this bit divisible by 4 here, but this bit is divisible by 2. So the whole thing, so since 2 goes into n plus 1, that means that 8 goes into 4 times n plus 1. So the original statement is true. I just really like that proof. So here's one for you to do. slightly easier, I think, I hope. It says if x and z are even numbers, then 4 divides x minus 7 squared. So what you need to do is rewrite x and z as even numbers, like I said at the top, and prove that when you do that subtraction and square it, you get something that 4 goes into. Be aware, x and z are not the same numbers, so you can't write them both as 2n. You have to give them different names. Have a go at that. This last bit of the video is just for fun and interest, because I think it's one of the neatest proofs, but it's not on the IB syllabus, as far as I can tell. So I'm going to prove that root 2 is irrational. And this is called a proof by contradiction. And it works like this. So what I'm going to do is I'm going to assume the opposite. I'm going to assume that root 2 is rational. And I'm going to prove that that can't be the case. This is just a really, really great demonstration of the logic of mathematics. So here we go. If root 2 is rational, that means root 2 can be written as a fraction, p over q, such that, and this bit is important, p and q have no common factors. No common factors. Or we could say that the GCD of p and q is 1. So the greatest common divisor, the highest common factor of p and q is 1, because they don't share any common factors. Well, what does that mean? Well, let's take the steps, root 2 equals p over q. Let's just rearrange that a little bit. A bit of basic algebra. That means that if I square both sides, I get 2 is equal to p squared over q squared. Or 2q squared is equal to p squared. Well, that means if p squared is equal to 2q squared, then that must mean that this side, both sides of the equation, are even. And in particular, p squared is even. Probably should have made it clearer that p and q are whole numbers. They're written as a fraction. They've got to be whole numbers. So p squared is even. So I'm going to rewrite, well, that means if p squared is even, it means p is even. And if p is even, I can rewrite it. I'm going to call it 2r. So I'm going to set p to be 2r. I'm going to substitute that back into my equation. So I've got 2q squared is equal to 2r all squared. And again, just a bit of basic algebraic manipulation. Expand out the brackets on the right hand side, divide both sides by 2. And now I'm in a similar position to what I was before, only this time, so again, both sides are even. Only this time it's clear that q squared must be even if it's equal to 2r, which in turn implies that q itself is even. But my initial assumption that I could write root 2 as a fraction p over q with no common factors prevents both p from being even and q from being even. That's not allowed. Since the GCD of p and q is 1, by definition, by assumption, then it's impossible for p and q to both be even. Which is a contradiction to our original assumption. Our original assumption was that root 2 was rational. So therefore, Root 2 cannot be written as a fraction, and therefore it can't be rational. And often when we're writing mathematics, we put a little square at the end, sometimes nicknamed a tombstone, to say that we've proved what we set out to prove. So I hope you found that interesting. Don't forget to do the last little exercise from here, and I'll see you next lesson.